Swayam Prabha. Digital India. Educated India.
So in the hollow shaft, remember, you don't have no material here, so it's a hollow, it's like a pipe. You have a pipe, outer diameter or outer radius and an inner radius over here. So in the inside, since you have no material, of course you cannot have any shear stresses or the shear strains. So your minimum amount of shear strain, it is going to happen at the inner radius R1, right? And the maximum is going to happen at the outer radius, which is your R2 over here. So if, just piggybacking on what the expressions which we wrote in the last couple of pages over here, if I have to write the expressions for this one again, so here what I'm going to have is my gamma minimum. It is going to be what? Gamma minimum is going to be R1 times phi divided by L. Remember, the general expression for gamma was what? Gamma equals to rho times phi divided by L. And what I recommend, sorry to take a pause, what I recommend while deriving these equations is that please go and grab a notebook and a pen. You have to write these expressions as we are going through this lecture to understand, to appreciate, because towards the end you will see we will have a bunch of equations, and only if you start to write and understand them, they are going to make some sense. So we have the gamma minimum here as R1 phi over L. So just for your aid, if you have just gone and grabbed your notebook and a pen, so let me write the expressions which we just derived in the previous page, the general expression for the solid shaft, which we wrote for the solid shaft, right? This is the hollow shaft or hollow tube, right? So for the solid shaft, which we wrote, the expression was gamma equals to rho times phi by L. We had the gamma max was happening at R rho phi by L, right? And using this, we derived the relationship that gamma equals to rho times R gamma max. This is what we wrote a page before, right? So now if you are starting to take notes from this point onwards, you see what I wrote over here. Following this relationship, I wrote this one for the inner radius R1, and also for the outer radius I'm going to have gamma max is going to be R2 times phi divided by L over here. Now if I use these two expressions again, similar to what I did over here, what I can write is gamma minimum is going to be R1 by R2 times gamma maximum, right? So these relationships over here are for the solid shaft, and this is for the circular tubes where you have an internal radius R1 and an outer radius R2. So let me just highlight these expressions as well. So these are two of the important relationships also which we saw over here, right? Okay, so now that and the summary of these ones is given as well. This is what we derived, that gamma min R1 phi by L, gamma max R2 phi by L, and this is the relationship after you take the ratios. Now coming back from strains, we are looking at strains over here. Gamma is the strain, right? What automatically pops up in your mind that there must be some associated changes with the stresses, right? So remember that for the stresses, and since we're talking about shear, the shear stress is tau. So for tau, if you recall the fundamental relationships, the relationship we have for tau is that before we go ahead and look into these figures and how things change, we have the very fundamental relationship for tau, that tau equals to G times gamma, valid anywhere and everywhere. You can't tinker around with this, right? Now if you go back and to the previous page, the expressions that we wrote one expression for gamma for the solid shaft, we wrote the expressions for gamma minimum and the gamma maximum for the hollow tube or the hollow shaft that is there, right? Now if you use this fundamental relationship, how do the relationships look like? Now we know that tau equals to G times gamma. So for here, what is my tau max going to be? Remember, my gamma max was R P times L. So that automatically tells me my tau max is going to be G R P by L over here, right? And so this is the maximum tau which is happening at the exterior over here, and at any general point rho, at any general radius rho, what I'm going to get is my tau is going to be G rho P divided by L. Now again, correlating these two over here, these two expressions, what I get is the generic expression that tau at any point, it is going to be rho divided by R tau max, right? This is for the solid shaft, right? Now for the hollow shaft, how are the expressions going to be? Very similar to this one. You can already imagine that here my tau max is going to be G R2 P divided by L, right? Tau min is going to be G R1 P by L. Now again, if you use these two relationships, what we will get, your tau minimum is going to be R1 by R2 tau of maximum. So this is also a fundamentally important relationship that is there, right? So these expressions, so the bottom expressions, these ones are for the solid shaft, right? And the ones which we just derived over here, these guys over here, are for the hollow shaft or tubes, right? So these are the fundamental relationships which we just saw for the shear strains, how shear strains are related to the angle of twist phi, how the strains are related to the stresses. We know that tau equals to G times gamma. So how now the stresses are related to the angle of twist phi and the entire length and the radius where you are looking at, right? Now extremely important to now visualize that what is actually going on in this entire member, right? So I have a summary for this particular slide as well. This is the summary of what we just wrote, that tau equals to rho by R tau max, and this is the tau minimum equals to R1 by R2 tau max. This is the expressions which we just saw in the previous page, and I highly encourage you that while going through this lecture, you write out these expressions as well, so it gets ingrained in your memory, right? Now coming back to just trying to imagine how this tau varies, right? So as you see in this figure, and as we just derived as well, that the maximum tau happens when rho equals to R, that is at the extreme periphery where you have the tau max, and at the center where rho equals to 0, this expression vanishes, tau equals to 0, and in between you have the linear variation. And why is it linear? Because this varies linearly, tau varies linearly with rho over here, right? Now if you try to imagine this, if you try to now take a look at the shaft, take a look at the solid shaft again from a kind of a zoomed out perspective, what you essentially see is this, right? So if you have this solid shaft, what I'm looking at is, say, an element at the exterior. Now when I'm taking a look at the element at the exterior point, now we have to imagine that all these elements, as we discussed, are in a state of pure shear. This is a state of pure shear. So that means that if I have this tau over here, to balance that one, because your Fy, summation of Fy equals to 0, remember equilibrium. So that means that I must have a tau over here, right? Now this tau and this tau, if you take a small block of an element, it forms that in equilibrium, and it gives rise to that couple. To balance that, I must have a tau on top and a tau on the bottom over here, right? So now the interesting thing is, and since we are looking at an exterior element, all these taus are nothing but your tau max, because we are looking at the outside periphery over here, right? So now as we saw that, and this element that you took, instead of taking on the outside, if you keep on successively going inside, right, these taus are going to change. These taus are going to go successively reduced till it becomes 0 over here. So if you take a cross section and if you look on the inside, if you just try to have a zoomed in view, how does this shear look like? It looks something like this. At the exterior, see, this is that exterior element, this is that tau max I was looking at, on the outside. So this is the tau max, this is the tau max over here on the outside element, which you can see over. This is how the shear varies, tau max and tau max. And as you are going more and more inside, tau reduces linearly with rho till you reach the exact centroid, which is this particular point over here, where your tau becomes equals to 0 and you have a linear decrease. So this tau essentially varies from outside all the way to the inside point that is there. Next, what we are going to look at are the very famous and very well known torsion formula. Right? So we have until now established the relationship between the strains and the stresses and the phi, the angle of twist. Remember, phi is always the angle of twist which is happening at the cross section, at the very ends of the cross section where it twists. So at this particular cross section, by how much it is twisting, and the length of the shaft we are looking at, and of course the modulus of the shear modulus G. Next, what we are going to look at is the torsion formula. Now, what do I mean by the torsion formula? Let me just begin with that. So, with the torsion formula, and let's focus on the figure which is below over here. Remember, this was the shaft in which I had applied this torque T, which was being applied over here, right? So what the torsion formula essentially tries to do, it tries to establish a relationship between this phi, the angle of twist, with this T, the torque that is acting. The formulas which we just looked at before were relating your shear strain with the phi, your shear stress with the phi, and so on. We have not yet derived a relationship, a direct one-to-one relationship between this angle of twist phi. Let me write this again so that you remember. So this is always my angle of twist, right? The relationship between the angle of twist phi and the applied torque T that is there. So now let's go ahead and see how to derive that, right? Now I would like to draw your attention to this figure on the top. What you are seeing in this figure is again the solid circular shaft that we are looking at, right? So in this solid circular shaft, at a distance rho, at any random radius rho over here, I have taken a small element which has a cross sectional area. For this element is dA, right? And say this element, since it's in pure shear, say this particular element is having a torque which is tau, which is acting on that one. So what is the force which is acting on that element? You guessed it right, force is nothing but stress times the area. So the force acting on here is going to be tau times dA, right? So if the force is acting at tau times dA and the distance of this element over here from this particular point, from the centroid, is rho, right? So what is the moment that this particular element is imposing about the center? So since I'm working with a very small element dA, my very small moment which is imposing, it is going to be, say, dm over here, right? So I can go ahead and write my dm as, it is going to be tau times dA, which is the force, right, times rho, the distance, right? So what is going to be now the net moment, or the total moment, which is essentially my torque? This is the moment of that small element, and the net moment caused by each of these small elements is going to be my torque which is there. So my torque T is going to be integral over dm over the integral over the entire area of the cross section that is there. So we can write this as integral of tau rho dA, right? Now let's keep it at here and let's look at some of the relationships which we just derived. If you had a chance to write them as well, I encourage you to look at your notes, but let's just write it down, some of the expressions which we just derived in the pages before, so that we can directly make use of that here. Now I'm going to hold off over here. I'm going to carry on later after I have a chance to write the recap equation. So if we just do a quick recap, and you can refer to your notes as well. In the recap, remember that what we had derived, that our tau at any general tau was simply rho divided by r tau max. We had derived this one before, right? Now if I go back and put this in this particular expression, what I essentially get is that my t becomes equals to integral rho by r tau max rho dA, right? Now I can pull tau max by r. My t, I'm applying a constant torque t, so the tau max is maximum at the periphery, so I can pull tau max by r outside. So what I'm going to get over here is tau max by r integral of rho square dA. Does this ring a bell? The last expression, rho square dA. Think for a second. What was rho square dA? You have studied this in your +2. Rho square dA is nothing but the polar moment of inertia, right? So rho square dA, this expression that we just derived over here, right? This is the polar moment of inertia, usually represented by the symbol J. So if I have to further simplify this one now becomes my tau max J divided by R over here, right? So if I have to, sort of rearrange this expression, what I get is my, let me mark this symbol properly, tau max becomes equals to T R by G, right? And similarly, as you can understand that this is the maximum torque. So how the maximum torque is related to the applied torque T through the outer radius r over here and divided by the polar moment of inertia. Now this is the tau max. So how will tau be related? Very simple. Tau will be also linearly related with rho. So this maximum happens at the outer periphery r. So at any intermediate rho, if I'm taking at any intermediate radius rho, so this can also give me the expression that you're at any place tau, it is going to be T times rho divided by J over here, right? Now coming back to the first expression which we just derived over here. Now remember that when we were doing the recap, let us write also the another formula for the tau max which we had looked at. What was the other formula for tau max? The other formula for tau max, so let me maybe draw the border over here so that it does not mingle with the rest of your expressions, right? So tau max from gamma max, remember gamma max was equals to G R phi divided by, gamma max was R phi divided by L. So tau max will be G R phi divided by L from the relationship between the stress and the strain. So tau max here was G R phi divided by L, right? Now if you come back and if you substitute this expression over here, what you will get is G R phi divided by L equals to T R by J. So in this expression, your R and R goes for a toss and you end up with a very beautiful relationship which is known as the torsion formula. So if I again rearrange this one, what I get is my phi equals to T times L divided by J times G. This expression is known as the torsion formula. So let's just write that down and talk about it for a few minutes. So this is the torsion, and appreciate the importance of this relationship. What you have over here, it relates the angle of twist phi at the end, which is happening over here, to this torque. It is not as straightforward as some of the expressions that we derived before, though we will see later they're analogically similar. But remember, when for the axial load, that delta equals to PL by AE, we got it, in a jiffy. It was very easy to derive, very quick to derive. Whereas here, to derive that this fundamental relationship, we first had to start with the strains gamma. We went to the stresses tau. We established the relationship between tau and T over here, this particular relationship over here, this one over here, right? This is also an important relationship. Let me maybe mark this one as well, right? This relationship, and eventually after using all these different relationships, we ended up with this particular expression that your phi equals to TL divided by J times G. So this is the torsion formula, right? Please write it down, write it a couple of times so that it gets ingrained in your memory. So the angle of twist phi is equal to the applied torque T times the length L divided by the polar moment of inertia J times the shear modulus G, right? Now a couple of notes about this polar moment of inertia J. I am sure you would remember, but let me just write that down as well. So for J, remember J for solids shafts means it's completely solid. There is no hollow section. Solid circular. If you have a solid circular shaft with a radius r, what does the value of J? The value of J is pi r raised to 4 divided by 2, right? Let me erase that here and put another marker. Yeah, pi r raised to 4 divided by 2. And suppose you have a hollow shaft. Suppose you have a hollow shaft which may be outer radius r2 and maybe inner radius r1. How does J change? J becomes equals to your pi r2 raised to 4 by 2 minus pi r1 raised to 4 divided by 2 over here, right? These are some of the important things to remember when you will solve some of the problems. So this is also an important relationships as well as this one. You probably remember this, but thought I will just write it out over here, right? So now that we looked at so many different relationships, I really encourage you to write it out on your own as well. In addition to that, if I just have to put you know so this is the torsion formula which we just derived. So this was the TR by J. Remember, let me just quickly go back to the previous page. This is the TR by J, and this is the torsion formula TL by JG that we looked at over here, and this intermediate, that the tau for a general case is T rho from here, TR by J and T rho by J over here, and this is the famous torsion formula that we looked at over here. Now if you have to bring all the relationships that we studied together, this is that entire summary of this lecture, if you may. We looked at an overall solid circular shaft in which we derived this relationship, that your first to start with the shear strains gamma max r phi by L. You can use this as well to derive that gamma equals to rho divided by r times gamma max. We derived this relationship for the hollow shaft or hollow tubes where you have no material over here, how the gamma min is related to the gamma max and how the tau min is related to the tau max. And last, what we looked at was the torsion formula, where you end up with this relationship which gives you a one-to-one correspondence between the angle of twist phi, applied torque T, through the length of the shaft divided by the polar moment of inertia times your the shear modulus G, right? Now that we have all these different formulas, all these different skills which we just learned, next we are going to look at an application example.